Introduction.
Yeah, you did it. You're fine. I'm going to mute me. I'm going to mute myself now.
Okay.
Okay, you ready, Andy?
Sure.
Here we go.
The broadcast is now starting. All attendees are in listen-only mode.
Good day, everyone, and thank you for attending our How to Model Light Sources in TracePro webinar. My name is Andrew Knight, Technical Sales Manager here at Lambda, and I have with me Dave Jacobson and Mike, what's your name again? Mike Garvin, who is our VP of Sales. The format of the webinar will be a presentation of the various illumination sources available in TracePro, their best use, and examples of how to implement them. This will last approximately 20 to 30 minutes. The presentation will be followed by a question and answer session. You can ask questions at any point during the presentation using the question window on the GoToMeeting control panel. We'll address all the questions after the presentation part is over. And with that, I will turn the meeting over to David. Thanks again for joining us.
Thanks, Andy. My slides advancing properly this time?
Let me check.
We should be on the format?
Yep.
Okay, excellent. Okay, well, like I said, good afternoon, folks. My name's Dave Jacobson, Senior Applications Engineer here at Lambda Research, and I'll be your presenter today. Today's webinar, we're going to look at light source modeling in TracePro. So some of the goals of this afternoon's session is we're going to learn about some of the light source modeling tools in TracePro, some of the different sources, including grid, file, surface, and bitmap sources. I'm going to try to give you a little bit of insight on the best method for modeling a given light source in TracePro. Try to show you how combination of sources can be used to model more complex sources, such as an arc lamp or a diffuse or an overcast sky. Then I'll show you a comparison of some measured versus modeled data for a pulsed xenon flash lamp that we've worked with. And also I'll touch on some of the TracePro utilities that are useful for source modeling, including the surface source property generator utility, the IES Import Utility, and the Bitmap Source utility. And then at the end we'll have a question and answer session. So as Andy mentioned, please feel free to submit any questions at any time during the webinar using the question window on the GoToWebinar control panel. So with that, let's get started. So the question is, what types of sources can you model in TracePro? The answer is pretty much anything. Some examples here: LEDs, OLEDs, arc lamps, filament lamps, lasers, fluorescent lamps, the sun, the sky, fluorescence. Really almost anything that emits light you could model in TracePro in one way or another. As I mentioned, there's 4 basic types of sources in TracePro, and we'll cover these one by one here as we go along. First is a grid source, then there's file sources, surface sources, and bitmap sources. A grid source is basically a grid of points that emit light, and it can be rectangular or annular. Typically, it's going to be a 2-dimensional source. So this means it's good for planar sources that have a well-defined boundary, sources that emit in a Lambertian or uniform manner, and it can work with either monochromatic or polychromatic sources. Where it's really not well suited for would be something that has a 3-dimensional shape to it, because as I mentioned, it's a 2-dimensional plane that emits light. And you may not be able to model some of the more complex angular distributions as well. Some good examples of sources that lend themselves well to a grid source would be the output of a fiber optic or a laser diode. So here we have a setup example for a grid source for a laser diode. I'm just going to turn my pen on here. And we see here we can define an X and a Y half width. We can define a grid pattern. In this case, rectangular makes sense. We can click over next to the beam setup tab. In this case, we're doing a laser diode, so we want a Gaussian profile on the spatial, define the X and Y beam waste, and then also a Gaussian distribution on the angular. So 17.5 degrees in the X, 7.5 degrees in the Y. Run this ray trace, and these are the resulting images we'd see. We trace the light to a target. We see an irradiance map here. We see the elliptical profile resulting from our definition there using the Gaussian half-widths. And we also see our beam profile, where it's narrower in one axis than it is in the other. So again, not a good way to, it is a good way to model, like say, the output of a laser diode. Next up, we have file sources. The file sources are a text file containing ray information. And I'll show you an example here in a second. A file source is very good for either a planar or a three-dimensional source. Very good for sources that emit with complex angular distribution patterns, because you can have light varying in azimuth and polar angles. Sources, they're good for sources that can be modeled monochromatically, as typically most of the file sources are defined at a single wavelength. Also excellent for sources that have lenses or structural elements or complete optical systems, because the ray files are generated by actually measuring a complete system. So if you had an LED package or a luminaire package, and you scanned that with a Gaussian photometer and saved all that ray data. So it takes all that structure into account, so you don't necessarily have to model that in your program. You can just insert the ray file or the file source. Some of the considerations were, as I mentioned, they're typically defined monochromatically, so single wavelength. You can work around this. You have multiple ray files at different wavelengths. You can do that. They're also not a good choice if the emitted light's going to interact with the source. Because as I mentioned, it's a file source. It has no structure or no three-dimensional qualities to it. So it doesn't have material and surface properties, so there's nothing for the light to interact with if it stays reflected off of your optic. Some examples where you'd see file sources, LEDs and luminaires. IES files, which those of you working in the lighting industry may be used to working with, are an example of a file source or a ray file, just a slightly different type. Here we see a file source from an LED. In this case, it's an Osram Golden Dragon Plus LED. Downloaded the file source right from the Osram website. They have it available in a TracePro format. Also downloaded a SolidWorks drawing, which I imported into TracePro, of the LED package itself. In this case, the LED package has no properties, no material properties, no surface properties. It's shown in the model for reference only. Ran the ray trace. We see the angular distribution here. We also see an irradiance map. And as you can note, it's monochromatic. This particular one was traced at yellow wavelengths, even though this is actually a white LED. Here's an example, as I mentioned, of what's actually contained in a file source. And you have X, Y, Z positions for the starting positions of the rays, X, Y, Z direction vectors for the rays, and a flux. And these files can be over 1 million lines long. They can be, very lengthy downloads, long time to run at times. And as I mentioned, typically they're monochromatic only. Here's the little problem I mentioned that can happen with ray sources or file sources. If you have light that could interact with the body of say in this case an LED, what I did here is I set up the ray file. Some of the rays are totally internally reflected inside here by this little TIR hybrid lens it designed a couple years ago. And I used ray sorting in TracePro just to show a small percentage of the rays that are hitting the LED dome. If I actually went and looked at like a flux report, I could see that about 0.1% of the initial flux is impinging back on the source. Relatively small value, but in some cases it may be a larger number, and it may be something you have to watch out for. So if you're worried about light impinging back on your source or interacting with your source, then you may have to go do a little more detail and actually model the source as a three-dimensional solid. Now we're going to look at surface sources. Surface source is probably the most versatile source in TracePro. Good choice for a detailed source model where you're modeling all the structure, the packaging, glass, plastic, the surface and material properties. Good choice also, if you have a source that emits with a complex angular and spectral distribution pattern. So you can define a surface source property as having polar and azimuth angles and wavelength dependent emission. So you can model the spectrum of that lamp or that LED. Then you can start looking at things like true color and CIE coordinates and color temperatures in TracePro. It's also the way you want to go if you're modeling the interaction of light with your source and where that is important, and you can actually model the structure of, say, an LED or an arc lamp or whatever your source is. Some of the considerations, well, based on what I just said, the models are going to be more complex to make. You have to define all the parts of this model. And you need accurate material and surface properties to do this. So again, some examples that you might see where a surface source would be useful. An LED, lamps such as arc and filament lamps, or if you're doing a complete optical system, whether it's a luminaire or a lens system or an imaging system, you'd want to be looking at surface sources where you're modeling everything in good detail. An example of a surface source property here. And as you can see, the emission can actually vary as a function of temperature, wavelength, polar angle, and azimuth angle. So it gives you a lot of flexibility in how you define this property. One thing I want to note too here is that the units need to be consistent when you're defining a surface source property. If you have spectral data, more often than not that spectral data is going to be in radiometric units. It's going to be watts per nanometer or something along that lines. So if your spectrum is in radiometric units, you want to define your emission quantity here. And when you actually define the property in TracePro, you see you have the option of radiometric or photometric terms. You want to define that in the same terms as your spectrum is. Otherwise, you could see some unexpected results. And if you want to work in lumens for your emission quantity here, then what you really need to do is convert your radiometric data for your spectrum to photometric data by multiplying it through by the photometric curve. So just a thing to note is keep the units consistent. So here's that same Osram Golden Dragon LED. In this case, I put a small surface source, a small object in the center to represent the surface source, or the dye of the LED. The angular distribution here, same angular distribution we're going to see from the ray file, because we based this surface source property on the data sheet for the LED. So it's based on a complete measured LED. And as you can see here, we now have true color. We see that this is actually a white LED. And if we were in other modes of TracePro, we could look at the color temperature or the CIE coordinates for that as well. Still in this case, this LED body was modeled. There's no properties applied to it. It just has the surface source properties because they're already taking into account the LED body because we used the measured data for that. And this was generated using the surface source property generator utility, which I'll touch on towards the end of this webinar. Last source type we have is bitmap sources. And bitmap sources let you make file sources from image files such as bitmap, GIFs, JPEGs, movies, and you can use those in TracePro. We have a bitmap utility, bitmap source utility that converts an image file to a TracePro ray file or file source. Some of the considerations here, the resulting file sources can be really large. So it can take a long time to load them into TracePro and a long time to run the ray traces. An example of when you'd want to do this is if you wanted to trace an image through a system in TracePro, say a lens system, you wanted to see if you had any ghosting or glare, things like that. So here's an example. Took the image here of our cat, ran it through the bitmap source utility, generated a ray file, which was actually placed right here in TracePro. That was run through the lens, and here's the resulting image. It's a little pixelated. I could trace more rays here to really get that to be a smoother image. But it's for demonstration purposes here. Shows you can do actually tracing images through a system in TracePro. So another option for for a source. Okay, now what I want to look at is I'm going to take a single model and show the effect of using 4 different sources in that model. First is we're going to work with this same TIR hybrid lens. Again, this is a design we did here last year at one point for a demonstration. And we're going to just change the source we used for the modeling. In this case, it's a point source. Point source is just a variation on a grid source. We set the diameter or the radius of the source to be very, very small. So all the rays are coming from a single point. You can see here on our irradiance map, we have a very tight focus. And our candela plot, you can see it's very tight. Not a real world use. I mean, LEDs don't emit all their light from a single point. So the next step would be, actually, let's make the LED, model the LED as a 1 millimeter by 1 millimeter grid source. Very similar, we just change, we actually give the source now some actual physical size. And you can see if we go right between the point source and the grid source, we have a much larger spot on our irradiance map. Everything else has been kept the same in this model. We see a little more spread here in the candela distribution. So we're starting to see something that's closer to real world now, even though it's a relatively simple source model. It's a grid source with a probably I think about a plus or minus 60-degree angular distribution. Now we took the ray file for that LED. This is again that Osram Golden Dragon Plus. Downloaded the ray file from the Osram website. We can see here a little better resulting image in the irradiance map. Candela plots look similar. So again, we're getting better. We're refining the model here. Another version is that same lens using a surface source property placed here on the LED body. Again, very similar results now to the file source, but this would give you the ability to do polychromatic type measurements as well, because if we define the actual spectrum of the LED. So just a look at ways you can use different sources in a model and how your results might change depending on what source you picked. So I want to talk now about actually increasing the complexity a little bit. So far our models have been pretty simple. They've been a single surface emitting light at a given angular distribution. But what happens if you've got something that's a little more complex? How could you go about that? Here's an example. It's a 1500 watt xenon lamp, ceramic body, elliptical reflector, and has an arc here between these 2 electrodes. The simplest way to model this arc would just be use a cylinder to represent the arc. And not a bad way to do it. I've used that method numerous times myself. But there's also a better way we could do it. We could look at the actual luminous intensity distribution on this arc. If those of people that have worked with arc lamps would know, you have a hot spot, which is right here, sitting on the cathode. And then as you move away from the cathode, the luminous intensity drops off. So what I've actually done in this model is I used SolidWorks and I created this series of nested solids. And you could do this in TracePro as well, but created this series of nested solids. And each one of these has a spectrum and then a different luminous intensity to it. So it drops off as you go further and further. So if we ran this through a series of lenses through an imaging system, we'd actually see the hot spot on the cathode, which is more realistic. So if you were working with a DLP or a projection system and you wanted to image just that brightest spot of the arc, you could do that in TracePro, as opposed to modeling a very simplistic arc that's just a cylinder between the 2 electrodes. Then you don't get a feel for where that hot spot is. So something that, a way you can kind of step up that accuracy. Another thing I could show you here is a spatially varying source. Now, surface sources in TracePro have a fixed, they assume that the distribution of light is uniform across the surface. But what if you want to model something like an overcast sky, where the light coming from the horizon has a lower intensity than the light coming from the zenith? So it varies spatially as you moved across the sky. What you can do, there's a way you can do this in TracePro. It takes a couple steps, but it's one of those things that you can do once and then save it for use in future models. I have a formula here basically saying the luminance varies as you at a given angle above the from the zenith, or above the horizon actually, and it's the formula is 1 plus 2 times sine of theta, or over 3, and it's going to vary as a function. As you go up, the luminance will increase. So if we take that formula and actually make a surface source property in TracePro, where the emission is the results of this formula for each angle from 0 to 90 degrees. The only thing to note is that in TracePro the angles are a little bit different in that this formula assumes a zenith at the 0 degrees is at the horizon. In TracePro, 0 degrees would be at the zenith. So you just need to flip your results around to get the right results here. So we see its highest, the emissivity is the highest at 0, so that'd be pointing towards the zenith, and then it's the lowest pointing towards the horizon. And I gave it an emission value of 65 watts per meter squared. So what I did in TracePro then is I defined this hemisphere to be my sky, and in this case it's much bigger than my model. I think this is like 10 meters or so in diameter, but you could make this as large as the model you need to encompass the model you're working with. I put an object here at the center of this hemisphere that I'm going to use as my emitter, and what I'm going to do here is I'm going to apply that surface source property, and I'm going to trace rays from this source to this hemisphere. And if you remember, these rays are going to vary depending on the angle, so the highest flux rays are going to hit the zenith, the lowest flux rays are going to hit the horizon, and they'll drop off as it goes between there. So again, trace large number of rays, there's only a small portion shown here, to the inside surface, the hemisphere. So now we actually have that distribution across here. Then we can get an incident ray table for that inside of that hemisphere. And then using that incident ray table and then go to File, Save As in TracePro, you can save the incident rate data, and it gives you the option here of export to source file format and reverse source ray direction. So what that will do now is that will now make a ray file that's actually pointing in this direction. So it's coming in from the hemisphere, so it's going to act like the sky. The values here, the emission from here is going to vary. The highest values were here at the zenith, the lowest values were here at the horizons. So we've now actually created a spatially varying light source in TracePro. It's taken an extra step, but it gives you a lot of versatility because you could change this formula here if you want a different type of distribution and repeat the process. So here we see in TracePro, here's the rays, our file source. We've imported it into a new model, and the rays are actually going down in this direction towards a target here in the center. And here's our results. We have a little bit of error out at these very low angles here, but in reality, through almost 80 to 85 degrees of this, it tracks quite well with the calculated values from the formula. So a good way to do something like that, to think of it, if you need something that's spatially varying, think if there's a way you can do it by an angular variation and then just reverse the ray trace. Now what I want to look at is actually some measured data versus simulation data. We'll look at an example here. This is a PerkinElmer FX1150 short arc xenon flash lamp. Folks at PerkinElmer were nice enough back in October, November this year to let me go up and use their optics lab and actually take some measurements on a lamp like this. I'll show you a bit of the structure of the lamp. We have a window We have an arc between these two tungsten electrodes. We have a little trigger probe. We have a lamp body that's made out of Kovar, and we have a white base here. It's of a glass material. So that's going to have some reflection to it. There's going to be some reflection and scattering due to the lamp sides. So we actually built the model using surface property data to create these types of surfaces. The other thing we looked at here was the arc itself. Now, the arc isn't a uniform distribution of light. You can notice here it's brightest right in the very center, and then it falls off as you move away from the center of the arc. You can see here too, here's the trigger probe, and here's the electrodes. They're just visible. This was taken with a CCD camera attached to a laser beam analyzer that was synced to the flash lamp so we could catch pictures of the arc as it was flashing. And here's the arc model we built in TracePro. You can see we have it's again built as a series of nested solids with the highest intensity right in the center and then falling off towards the edges. So we ran that model in TracePro versus we measured the lamp itself. The lamp is measured in two axes. One, we measured across this axis in a rotational plane, and we measured across this axis. So if we look at our results here, we can see we have very good agreement between the measured and the model data. You can see here this curve here actually corresponds to this measurement across the electrodes. So there's some shadowing due to the two electrodes. So if you just modeled this lamp without any electrodes or without any objects there, you'd be modeling something that looked more like this outer curve here, and you'd be missing the fact that in that axis across the electrodes it's actually a narrower emission. So a way you can improve your accuracy there is to have some of that structure in place. Also measured the spectrum of the lamp and use that to create a surface source property, the spectrum in TracePro. You see here, this is measured with a spectrometer at 0.7 nanometer sampling interval. Ran the ray trace in TracePro with a 2 nanometer sampling interval, and you can see again good agreement between the two versions. I want to wrap up this presentation portion with taking a quick look at some of the utilities that are available for modeling sources in TracePro. First up is the surface source property generator. Hopefully most of you had a chance to download this at one point and take a look at it, but very good tool for modeling light sources, for getting the surface source property information into TracePro. In this case, we took the data from a Luxian Rebel LED. We had the data sheet, and we cut and paste the spectral graphs and the wavelength distribution, the angular distribution graphs. So common information from an LED data sheet. And then it's simply a matter of doing left clicks with the mouse to actually trace out the spectrum and then the angular distribution here. And you can save that right here. We can just export that to TracePro. It'll automatically save this property. Some neat features here. It will give you the correlated color temperature and the CRI, the color rendering index of this spectrum here. Gives you a little representation of the color. This here, where it says units, can be a bit of confusion to some people. And this relates back to my earlier comment about keeping units consistent. This graph here is in radiometric terms. You're almost always going to see spectrums in radiometric terms. If you switch this over to photometric, which is the other option, that would assume that this graph now is in lumens per nanometer. Very rarely do you see graphs in lumens per nanometer. And it'd be the equivalent of multiplying this graph by the photometric curve. So it would actually look probably something more like this. And if you actually then looked at the color, it would probably be blue as opposed to the white that you're expecting. So again, just pay attention to your units. More often than not, you're going to be in radiometric units. Another utility here is the IES Import Utility. Those of you working in the lighting fields are probably used to working with IES files. TracePro gives you this utility to load those sources into TracePro itself. And all you do is you browse to your IES file and load it. And you can see here we have a three-dimensional representation of the IES file, or of the light from that source. And then it gives you the option of exporting either as a surface source property or a file source. You can save those and then go use those in TracePro. TracePro also gives the option of creating IES files from the Candela plots. So if you're working that and you have another program that you're using, say something like Lightstar from Oxytec, where you want to visualize the light source you've designed in a room, you could export the IES file and then load it into a program like that and see how it looks in an architectural application. And our last source utility here is the Bitmap source. And this allows you to you load a bitmap image here. One of the screens here, you define your scene information. So how big is this image in millimeters, horizontal and vertical? Where is it located with respect to the camera or to the imaging system? And then as you go through this here, you would also define the entrance of that imaging system. So where are these rays being traced to? And then when you click OK, it would generate a file source based on this information, which you could then go and install. And you could actually use it in any TracePro model you wanted. So you could create a series of bitmap images, and you could try them in different imaging systems or different models in TracePro. So they're not unique to a given model. So that ends the prepared portion of our presentation. What I'd like to do now is open it up for any questions that we might have. Bring Mike and Andy back online here. Again, feel free to send in any questions you have using the question portion of the GoToWebinar control panel. While we wait for questions, Mike or Andy, do you have anything to add?
No, sir. I just thank everybody again for attending, and that was a good job, David. And so far, I see we don't have any questions yet. We're certainly standing by to wait to see if any show up.
Even if there's something that somebody would like me to clarify a little bit more, we've allowed time, we can go back and do that. Yeah, okay.
Expand this. So we have our first question.
Yeah.
In the bitmap source, what is the light distribution coming from each pixel?
Well, each pixel is going to have an RGB. You're actually defining three wavelengths it's tracing at in the bitmap source utility. And actually, let me bring that utility up here. Let me just do this here while we're... So what actually happens, we go through Source Wizard, and this shows you a little introduction what's happening. Here's your scene, and here's your target. So we're defining our scene. Say it's 150 by 200 millimeters, and we're going to locate it at 1200 millimeters in front of our object. Then we can give it the target. So the example I used, we had a lens. The lens was located at Z is equal to 8 millimeters. We could define the plane. In this case, it's along the Z-axis. It's normal to the Z-axis, and the up direction's in the Y. And an aperture radius. So that's the aperture of the camera lens. Then here we can define the RGB value. So it'll look at this bitmap here, determine the RGB values, and trace rays, the distribution according to the wavelengths you've defined here. And then the angular distribution is going to be dependent on the target you've defined here. So It's not going to let me go back. So we defined a target of being 50 millimeters in diameter, so it will fill that aperture and use that as an angular distribution. So hopefully that answers that question there.
Thank you.
Okay. Again, any other questions? As we're waiting, I will note we will be archiving this webinar on our website probably within the next day or so. So feel free, if there's something you missed or you want to see again, you'll be able to download a copy of this. You'll find it in the webinar portion of the homepage of our website. We also have archived version of our previous webinars, including an introduction to TracePro 7.0, some of the new features in TracePro 7.0, including the new optimizer. We have one on the TracePro bridge for SolidWorks. And then we have several webinars specifically addressed to the new optimizer that's available in TracePro 7.0.
Okay, looks like we have another question. If I have TracePro, is there anyone who sells tutoring services or maybe will take on property design jobs? I think.
Yeah. Mike, do you want to touch on that one?
Yes, we do consulting all the time. We can actually set up where we do go-to meetings with you for tutoring, and we can also, if you had a whole bunch of PDFs with LED information, we could take that information and create a database for you on a per charge as what we're doing. So if you'd like, you can send an email to me, Mike Govin. I'm the VP of Sales. My email address is mgovin@lambdares.com. Specify what you'd like to have done, and I'll send you out a quote.
And what about if it was, say, for having surface properties measured, say like for scattering? We have contacts we could send them to as well, right?
Yes, we actually have a partnership with a sister company, Schmidt Industries, and they have agreed to, if we send them surface data, for instance, samples of 2 inches by 2 inches, they will do a BRDF output to us that you can directly import into TracePro as your surface property. If you want a photometric type setup taken of your light sources, we can do that as well. We work with radiant imaging for that type of capability, and we have radiant imaging sourced directly into TracePro as well as our file source possibility.
And what radiant imaging will do is take your, if it's a light source, and scan it with a Gaussian photometer and send you those images, or that as a file. See, we have another question here.
Yes, we do. It's for a surface source, can you limit the angular distribution of the rays? For example, if you have a source and a screen, can you limit the rays to lie within the screen?
Yes, you can do that. Let me just go back to my surface source here. Here's an example of a surface source property. Again, this is the one we used for the Overcast Sky. But as you can see, turn my pen back on. We can see here we have a polar angle column. And you can define the emissivity as a function of polar angle. So here, if I can draw over here, say we had a source and it's emitting light in this direction, and we wanted to confine the light into this angle. So say this is 45 degrees in each axis. What we could do is we could define a surface source property here where we'd have emission values up to 45, and then above 45, these could all just be 0. Or you could go 45, then 50 could be 0, and then it would interpolate everything beyond 50 as being 0. So yes, you can use the surface source property to limit your angular distribution. You could also do the same thing in azimuth angles as well. So yes, very easy to do that using this. And these are very easy to create right in TracePro itself. And we certainly, if there's questions on doing that, please feel free to drop us a note, and we can set you up with the information on creating custom surface sources. And the other easy way to do it is using the surface source property generator here, where you could define, this is a Lambertian output here, but if you had a an output that, say, was only roughly 20 or 30 degrees, you might have something that looks like that, and you could do that if you have it graphically as opposed to as in a text file. So several options for doing that. You can also limit angular distribution in a grid source as well.
Okay, we have another one here, David.
Yeah.
We have a radiant imaging sphere. Can we use the data from that, presumably, in TracePro?
Yeah. I'm not familiar with the imaging sphere from radiant imaging. Any experience there, Mike?
Well, if you would go back to the file source that shows what the file format is, which is the XYZ direction,
Yeah.
the XYZ cosine values, and the power, if your radiant imaging sphere gives out this type of data, right there you go,
Yeah.
then yes, you can definitely use it inside of
Right.
TracePro. That is our file format for the file source. Okay, so that's what, if you can output a file from radiant imaging, you can see it's in this format, yes, we can use it.
Okay. And I mean, like ProSource, which is one of radiant imaging software packages, has TracePro as an output option. So if the imaging sphere is running ProSource software, you should be able to get a TracePro format file from that.
Excellent. We have an additional question. What is the difference between grid, surface, and file sources, and how can we select the source?
Well, I guess to break it down in simplest terms, a grid is a flat surface that emits light. It's two-dimensional, and it's going to emit as a grid of discrete points. A surface source could be flat. It could also be curved, have any shape or format. A surface source is actually anything in your model that you want to turn into a source. And a file source it's what we're looking at here. It's a collection of ray positions and direction vectors. As to which one to use, that's going to come down to what you're actually trying to model. As we looked at here, here's an LED lens that could be modeled as, possibly as a grid source. Here it is with a file source. Here it is as a surface source. So sometimes it's more important on how you set up the source as opposed to exactly which one you choose. And it would come down to the ultimate, to the end goal. If I wanted to use this lens and I wanted to see color mixing and I wanted to see what's the color temperature at a given spot, I'm going to model it as a surface source because I can apply that spectral data to it. My last choice for this would probably be a grid source. LEDs don't emit light as a series of discrete points. A file source is a great option here, but it does have the limitation typically of being monochromatic, and it may not be the wavelengths you want to work with. And if it's saved in a binary format, which a lot of them are to cut down on size, you can't change that wavelength. So you're stuck. So for LED modeling, a lot of times I work with the surface source property, but also I'll look at ray files as well because they're based on measured data as well. So really it comes down to what your particular application is.
Okay. No more questions so far, everyone?
No. Here we
All
go.
right. Couple coming up. Let's see. Can we efficiently model a 3D scene, for example, a frame from a 3D movie, through a lens and get a good image on a detector?
3D, probably not. What you'd probably have to do is build it up as a series of slices, because if we go back to the bitmap source here, we're actually looking at this image at a single plane. To do something like that, you would probably need multiple file sources here on the input to represent the depth of the image. And you can also define multiple planes here just using incident lights instead of absorbed properties. So you might be able to do it. The efficient part is probably the bigger question. I think it's going to take a very long time to run the ray traces and to generate the ray files. As you can see, this was probably about a 15-minute ray trace in TracePro. So I guess efficiency is a relative term there. But I haven't thought of doing that, but just a quick off the cuff, I think it might be possible, but it would take some work. And then you'd have a series of images like this that you'd have to reconstruct in some external program to get that image.
Well, three-dimensional, right?
Yeah.
Okay. Hopefully that was a good answer.
Sure.
What would you use for direct solar light, I assume, to model the sun?
Right. Two options. One would be to use a grid source. That's actually a good application for a grid source. TracePro has a built-in solar angular distribution. If I go back here to my grid source, if we look here under angular profiles, you'd have the option of choosing solar there. So if you modeled a grid that overfilled your aperture and you set the angular profile to be solar, you could do it that way. You can also model there's a surface source property option in TracePro for solar for both angular and wavelength distribution. And when you create a surface source property and it asks you for angular type and spectral type, if we went to define and surface source properties, if I just did an example here on call webinar, and for spectral type we could choose solar, and for angular type we could choose solar. Click OK, and it's all in there. It has the emission of 1366 watts per meter squared. The solar spectrum would be, the spectrum of this would be that of the sun, and the angular distribution is that of the sun. So you could then apply this to an object in TracePro to represent the sun, probably a flat disk. You could have several of them across the sky if you wanted to trace one at a time. And we also have a utility that we're working on that should be coming out in the future that it will do some of this automatically. It will let you input your location and then the time of the day or the range of times that you want to look at, and it'll automatically trace the sun across the sky and save your results. So a couple options on doing solar modeling there. Okay.
Excellent. We have the next one up, which is, have you ever modeled a deuterium lamp source, and how would I get started doing that?
I've never modeled one, but from some experience, I think you would be looking at something similar to this, if you're actually able to get a distribution, because that deuterium is more of a glow type discharge. So what you'd probably want to do is somehow get a distribution. You may have to ask the lamp manufacturer for how's the distribution of that inside there, and then model that. But it's a larger glow type discharge, not as intense as an arc lamp like this, but I think some of the way to do it would probably be similar. I see the question about a 3D object, and it's not so much modeling. You can model a 3D object. We could apply a surface source property to every surface of an object. It's what are you looking to see through an imaging system, because right now we can look at an image or a true color on a radiance map on a on a flat surface. So you may not see your results as being a 3D image. But certainly they mentioned giving a call to tech support and just that's a good option. We can work with them one-on-one that way as well.
Yeah, yeah. I sensed the question might have been a little deeper than it looked at the surface. And that looks to be it for questions.
Okay.
We'll make one last call for any more questions, and if we don't get any, we'll thank you all again for attending, and hope to see you, quote unquote, here next time.
Yeah. Looks like that's it for questions. So. Yep. Again, from myself, thanks to everyone for attending this afternoon. Again, look for this to be archived on our website shortly, and we look forward to having you in our next webinar, probably in about a month's time or so.
Thank you all again.
Okay. Thank you. And thanks, Mike and Andy.